Good morning, chemistry students. I want to talk to you about intermolecular forces today. Intermolecular forces are important because without intermolecular forces, all matter would remain in the gaseous state. And that might seem kind of strange because we are so accustomed to the liquid state and the solid state in the world around us. And that's really entirely because of intermolecular forces. Now, the reason for the fact that everything would be in the gaseous state without them is that the kinetic energy of a group of particles, by that I mean their vibrations, jostlings, other movements, would tend to spread those particles apart. So let's say, for instance, you have a sample of a solid piece of matter. Maybe it's an ice cube or something. Okay? We know that ice doesn't remain in the solid state at any temperature. Now, if you could actually zoom in on a small scale and look at an ice cube, you'd see a whole bunch of particles. Okay? And the question is, what is keeping all of those water molecules, those particles, stuck together? You've also seen if you have a water droplet, and if it gets near another water droplet, maybe they're both kind of sliding across the hood of a car or something, they will kind of coalesce, right, into one bigger water droplet, right? What is it that keeps those water molecules stuck together that way? That's intermolecular forces. Now, we've talked a lot about the fact that, especially in a recent unit, that the hotter a substance is, the faster its particles are jostling around. So all of these water molecules are rotating around, vibrating, and just moving through space. Why would they stick together that way? You would think that they would tend to spread apart, right? Eventually they're gonna, if they have room, they're gonna spread apart, right? And but if you have a solid material, there's some type of attractive force between these particles that is keeping them stuck together. And those are intermolecular forces. So this is different than chemical bonds. We're talking about what keeps a group of particles stuck together. And that's intermolecular forces. Intermolecular forces are attractive forces that can cause particles to group up close together. And that would be the liquid state, or they can be locked into place, the solid state. And the stronger the intermolecular forces, the harder a substance is to melt and to boil. Okay, so with water, it doesn't have to be really, really warm for ice to melt, but you do have to get it quite hot for it to boil away and turn into the gaseous state. And that's because it's got pretty strong intermolecular forces. Higher temperatures are needed to overcome the intermolecular forces, right? We've got to get these particles, if this is water, we got to get those particles jostling around really intensely for them to start flying apart and boiling away. Okay, so we need a lot of kinetic energy to overcome those attractive forces. The physical state of a substance at room temperature, along with its melting point, the temperature at which it melts, and the boiling point, the temperature at which it boils, tell you about the strength of a substance's intermolecular forces. Okay, so what would you think has the stronger intermolecular forces? If you have three different substances, one of them is solid, maybe it's a piece of iron metal. Okay, so maybe it's some iron metal. You've got some liquid, and so maybe that's like some olive oil. It's kind of hard to draw olive oil. I'll just write it. And then the gas, maybe it's some helium gas. Okay, so which one of these do you think would have the strongest intermolecular forces? Okay, well, if you guessed iron, you're right. Apparently, there are strong attractive forces that keep iron atoms locked in place. Iron is in the solid state unless you get it really, really, really hot, over 1,000 degrees. Okay, so those atoms, the iron atoms, are locked into place because they have strong intermolecular forces. The molecules in olive oil have weaker intermolecular forces because they're not locked into place. They can kind of glide past one another. Okay, and helium has the weakest intermolecular forces of all of these three, anyway, because there's nothing that's keeping them stuck together. It's in the gaseous state unless you get it extremely cold. I think you have to get it down to something like 4 or 3 Kelvin before you can liquefy helium. And you actually can liquefy helium, but you got to get it really, really cold. One of the weirdest things that I remember finding out about, I don't remember how old I was, probably in middle school or something, was learning about liquid nitrogen. And liquid nitrogen is a strange substance that in theory is really, really easy to make. You got to get some nitrogen and just get it really cold, and if you can get it really cold, it'll liquefy. So this is a page from a book that I have that's titled Chemistry, and I follow its author on Instagram. That's actually called The Chemistry Book. And in 1895, there was a German scientist named Carl von Linde, and he took air and he basically figured out a way to cool it off using refrigeration. So this first paragraph right here describes something called the Joule-Thomas effect. You don't need to know about that, but basically he took compressed air and got it cold using some cold water pipes, and then he expanded it, which makes it even colder. So he's changing the temperature, and as he's changing the temperature from this Joule-Thomson effect, that's basically refrigeration. But he kept refrigerating it over and over and over again, and he got the air, so all the stuff that's in the air around us, he got it really, really cold, and eventually the air started to condense into liquid. Okay, so it's kind of strange to call air liquid, because air is, of course, a gas. That's what air is. But the stuff that's in air, all of those things that's in the air around us, started to liquefy. Okay, and then once he did that, he was able to separate out the components that are in the air, the oxygen and the nitrogen. Okay, so one of those things that liquefied helps stuff burn. That's oxygen. And some of this other stuff, you can't make really anything burn in it, the nitrogen. And they had, so it's kind of fascinating. But anyway, so I was really intrigued when I heard about liquid nitrogen, and I thought, that's crazy, how is that possible? And the whole idea is just get some air and get it really cold, and the intermolecular forces are going to take over. Okay, so focusing in on the nitrogen, since I was talking about liquid nitrogen, nitrogen in the air around us is a huge collection of diatomic nitrogen molecules that are bouncing around, right? They're flying through the air in all sorts of directions, randomly. They have different speeds, they're bouncing around, but in general, they're moving pretty quickly at room temperature. But the idea is, if we can get these things to slow down, right? If we can get these things to slow down, if there are attractive forces between them, as these things encounter each other, they will start to condense, and that means to group up. So condensation, that's what happens when you have some humidity and it's cold outside, and happens inside of your cars, like if you're driving to school or somewhere on a really cold day and then you breathe on the window, you get that condensation. That's the same type of effect. It's just really easy to condense water molecules. It's much You need much colder temperatures to condense things like nitrogen. But condensation is a result of intermolecular forces. So what is the cause of intermolecular forces? Something called electrostatic attraction. It's like gravity in that it's a fundamental force in nature. Gravity is one type of force. That's masses that attract each other. So Earth and the sun are exerting a strong gravitational force on you and me right now, and they're keeping us, the gravity due to Earth and to us is keeping us kind of stuck onto the Earth. We don't float off into space. But without gravity, we would float off into space, right? Without intermolecular forces, particles would drift apart. And it turns out these intermolecular forces are much stronger than gravity. It's a different type of attraction. Positive charges attract negative charges. That doesn't have anything to do with gravity. It's something different. Okay, this is electrical charges that attract. You might remember that when we talked about ionic compounds, I mentioned in passing that 99.9% of them are solid at room temperature. And looks like I didn't finish typing. Why? Why do you think ionic compounds would be solid at room temperature? That's because there are strong intermolecular forces that are present in ionic compounds. Negative and positive. Sodium plus, Cl minus, right? Cations and anions are strongly attracted to one another. So that's a great example to remember. Okay. Solid sodium chloride is a big crystal with alternating sodium and chloride ions, often 3 dimensions, and they all stick to each other because positive attracts negative. That's a type of intermolecular force, I suppose. It's a strange word to use because these aren't molecules and we're talking about intermolecular forces, but that is the reason table salt is solid at room temperature and not liquid or gas. Strong intermolecular forces. Now with molecular compounds, that's covalent compounds, you have a wide range of physical states at room temperature. The physical state of a covalent compound is much more variable. Okay, it depends on the compound and its particular intermolecular forces. So last week we covered 2 different types of molecules, polar and nonpolar compounds, and they have different intermolecular forces. The intermolecular forces that are present in polar compounds, there's 2 types, and they're actually not that different, and so we'll get into the subtleties of this tomorrow, but the intermolecular forces present in polar compounds are either going to be dipole-dipole attractions or something called hydrogen bonding. And we'll see that hydrogen bonding is in fact a type of dipole-dipole attraction. Okay, so those are the intermolecular forces that you could get in polar covalent compounds. Now, the intermolecular forces in nonpolar covalent compounds, I didn't finish typing my notes. This is something called London dispersion forces. And they are a result of instantaneous dipole moments that induce the same in nearby molecules. So we'll learn about these types of forces tomorrow, but what I want to do right now is to have a look at some elements data. Just looking at some elements on the periodic table. We're going to focus in on the halogens. Okay, so the halogens, these are nonmetals, and you've got fluorine, chlorine, bromine, iodine. So we're going to focus in on those 4 halogens, and we're going to look up their boiling points and what can we say about the strength of the intermolecular forces, the relative strengths anyway, of the intermolecular forces. I'm focusing in on the halogens because they are all nonmetals and they're all diatomic elements. So they're nonpolar diatomic molecules. And I left out one column, I'm sorry. We also want to have the state at room temperature. So the physical state at room temperature. Okay, so these I know, fluorine and chlorine are gases at room temperature. Bromine is a liquid, and iodine is a solid. Okay, so we can already start to see differing strengths of intermolecular forces. Which of these elements would have the strongest intermolecular forces? It's iodine. Solid particles are locked into place. That's what gives rise to the solid state. So lots and lots of iodine molecules are stuck in rows and columns of a crystal. In bromine, the bromine molecules are close together, but they can slide past each other. And in these two gases, kind of hard to tell which one has stronger intermolecular forces because they're both gases. But if we start looking at the boiling point of these substances, that's the temperature where the liquid becomes gas, we'll really have an idea about the strengths of the intermolecular forces. So I'm going to switch over here, pull up periodictable.com. Actually, let's do, that'll be fun. And we'll look at the halogens. So here's fluorine. If we click on fluorine, we can, if we hover over it, we can see that its boiling point is negative 188 Celsius. See here in the middle? Okay, so negative 188 Celsius is the temperature at which it boils, minus 188 Celsius. Okay, so that's a really, really cold temperature, right? Negative 188 degrees Celsius. Anything above that temperature, if fluorine is above that temperature, is going to be in the gaseous state. That's the temperature at which it goes from liquid to gas. How about chlorine? Negative 34 Celsius, its boiling point. Okay, so still pretty cold, right? Actually really cold for human beings, but much warmer than the fluorine boiling point. Here's bromine. It boils at 59 degrees Celsius. So positive 59 degrees Celsius. It's a liquid at room temperature, which is like 25 degrees Celsius. If we can heat it up to 59 degrees Celsius, it starts boiling. And then iodine, 184 degrees Celsius. Okay, so here we see a wide range of boiling points in different physical states. But if we imagine all of these things were really, really cold, starting at absolute zero, they're all solid. We start heating them up. The fluorine would boil away first because it boils at a lower temperature. We keep cranking up the heat on this stuff, then the chlorine boils away, then the bromine boils away, then the iodine boils away. The strength of the intermolecular forces is increasing. Stronger and stronger intermolecular forces. Okay, so that's the general idea. The higher the boiling point, the more the kinetic energy of the particles in the substance, and if you have to have a lot of kinetic energy for those particles to escape the intermolecular forces, that means the intermolecular forces are strong. So iodine has the strongest intermolecular forces, fluorine the weakest intermolecular forces. Even a really cold temperature has enough energy, in a sense, to make the liquid boil away. Okay, so that's a quick lesson over intermolecular forces. We are going to pick up tomorrow on the specific types of intermolecular forces, focusing in on dipole-dipole attractions and hydrogen bonding for polar compounds, and then another video on London dispersion forces.